All right, today we're going to dive deep into a really cool engineering story. It's all about how a team took a robot arm, a Universal Robot's UR5e, and pushed it to achieve truly mind-blowing precision. And trust me, this isn't some dry, theoretical exercise. This is a detective story. It starts with a huge, catastrophic failure and ends with a spectacular success. So let's get right into it.
You know what? Let's just start at the end. The big reveal. 0.088 millimeters, that was the final average error while the robot was tracing out a 3D cube. To give you some perspective, a single human hair is about 0.07 millimeters thick, so we are talking about an incredible, almost unbelievable level of precision. But here's the thing, it absolutely did not start out that way. Not even close. Nope, the project actually started here, with a 133 millimeter error. That is a disaster. We're talking over 13 centimeters, more than 5 inches off target. The robot was so inaccurate, it was literally crashing into the work surface, getting thrown completely off course by the impact. It was, for all intents and purposes, a total failure. So that's the central question of this whole story, right? How in the world do you go from a 13-centimeter train wreck to something that's precise down to the width of a hair? Well, the answer isn't about better hardware. It's about a really methodical journey through validation, physics, and one incredibly clever software fix.
Okay, so first things first. Before you can fix any problem in robotics, you absolutely have to trust your tools. And in the modern world, that means making sure your mathematical model of the robot and your physics simulation of that same robot are perfectly, and I mean perfectly, in sync.
So let's meet our two key players here. On one side, we have MuJoCo. Think of it as the robot's digital twin. It's a high-fidelity physics simulation using a fantastic model from the MuJoCo Menagerie. It's the virtual world where the robot lives, breathes, and deals with all the messy parts of reality like friction and contact. On the other side, we have Pinocchio. This is the analytical brain. It's pure math. It takes the robot's design and gives you the perfect, ground-truth equations for how it should move. So one is messy reality, the other is clean math.
And this right here, this was the first critical breakthrough. The team asked a very simple question. If we command the robot's joints to a specific set of angles, do our simulator and our analyst agree on where the robot's hand ends up in space? Now, at first, the answer was no. There were tiny bugs to sort out. Little things like quaternion conventions, classic robotics headaches. But once they nailed those down, the result was a perfect 0.0000 millimeter disagreement. They were in perfect sync. This created what they called a trust anchor. Now they knew their foundation was solid and they could start building on it.
So, with that trusted model, the first problem, the table collision, was actually an easy fix. They just moved the target cube's location. Simple enough. But even with a wide-open workspace, the robot was still wildly inaccurate. And this is where things get really fascinating, because it proves that even with a perfect model, you still have to go toe-to-toe with the relentless laws of physics.
The main culprit was a classic, and frankly annoying, robotics problem called gravity droop. See, a simple position controller is reactive. It only applies a corrective force after it sees that the robot isn't where it's supposed to be. But gravity isn't an occasional problem. It's a constant force, always pulling down. So, for the controller to generate a constant force to fight gravity, it has to allow a constant little error to exist. That error is what tells it to keep pushing up. It means the robot is always sagging just a little bit under its own weight.
And this wasn't some tiny microscopic effect. After they got rid of the table collisions, the team measured the error again. Get this, over 13 millimeters. A full centimeter of inaccuracy was caused by gravity droop and gravity droop alone. The robot was fundamentally fighting itself, and it was losing. A much smarter approach was desperately needed.
And this brings us to the real climax of the story. The big idea was, what if you stopped just reacting to physics? What if instead you could anticipate it? This is the feed-forward breakthrough. It's an elegant software solution that didn't just improve things, it completely changed the game. So here's the core idea in a nutshell. The new control command wasn't just, hey robot, go to this position. No, it was way smarter. It added two new proactive ingredients. First, a gravity compensation term. Using our math brain, Pinocchio the controller calculates the exact torque needed to counteract gravity in real time and just adds it to the command. It's like making the robot feel weightless. Second, a velocity feedforward term, which proactively cancels out the controller's own internal drag. So instead of playing catch-up with physics, the controller is now a step ahead.
And the result? I mean, just look at this chart. It's staggering. On the left, you've got the naive controller, stuck with that 13mm error from gravity droop. Then on the right, you add those two simple feed-forward terms, and the error just collapses. It plummets to 0.088 millimeters. That is a 1,500 times improvement in precision. And the most beautiful part? This was all achieved with smarter software. Not a single piece of hardware was changed.
So, with the core physics problem solved, it was time for the final showcase, the capstone demonstration. The challenge? Have the UR5e robot arm draw a perfect 10-centimeter cube just floating in midair.
And this is the whole pipeline, start to finish. First, you use inverse kinematics to figure out the exact joint angles the robot needs to hit all 13 vertices of the cube. It's like solving a puzzle backwards. Second, you generate these incredibly smooth mathematical paths called Quintic polynomials to connect all the dots seamlessly. Third, you execute that entire 24-second journey using that brilliant new feed-forward controller. And finally, you log every bit of data to prove just how well it worked.
And here's the final report card, that 0.088 millimeter average error we started with. Even the maximum error at any point never even reached a quarter of a millimeter. But here's the number I really want you to see, the max actuator torque. Only 16.5 Newton meters. By being smart about the physics, the robot achieves this incredible performance effortlessly. It's not even breaking a sweat. That is the signature of truly elegant engineering.
So, we've seen this journey from a 13-centimeter collision all the way to sub-millimeter precision, and it happened not with better hardware, but with smarter software that respects and, more importantly, anticipates physics. Which kind of leaves us with this one big thought. When our code can conquer the physical world with this much precision, what does that really mean for the future of automation? What new possibilities does this unlock in manufacturing, or surgery, or even space exploration? It's definitely something to think about. Thanks for joining me on this deep dive.